You're going to miss me, but they're going to doubly miss me. I'm missing like multiple people. No, Jacob, Jake. Okay, cool. Two people. All right, so now you guys tell me. Number one, I'm just going to ask for the answer. Let's go for it. 1. ST, good. 2. AT, 3. NT, 4. ST, 5. NT, 8. 6. AT, that's always true, right? 7. ST, good. 8. NT, 9. NT, actually, this one is directly from gas to vapor. Oh, sorry, from solid to gas. That's called sublimation, right? Where we at? 10? 10. AT, good. 11. ST, good. Guys, check with a different colored pen. It's not really for me, it's more for you, so you have to study. Right? Like, if you get it wrong, mark it wrong, go back, or mark the right answer so you can go back and kind of correct that misconception. Got it? Be honest with yourselves. Thank you. Where are we at? 12? 12 is AT. 13? AT. 14? ST. 15? NT. 16? ST. 17? AT. 18? Water can be made to boil at 105 by increasing the air pressure above the water. Let me do this demonstration. Atmosphere, like this. Okay, atmosphere. If I'm on top of Mount Everest, what's the atmosphere like? Sparse, right? Weak. Alright, so if I want to boil water, basically water boils whenever the atmosphere and water pressure meet, and they're the same. So if I want to push up on the atmosphere and I'm on top of the mountain, it's not going to take very much energy, right? Because it's light atmosphere, weak atmosphere. So weak atmosphere does not take very much energy to bounce back and then like push through. So do you think I have to boil water at a higher temperature or will it boil at a lower temperature? Lower, because it doesn't take very much, but again, atmosphere, where are we at? If it's really strong. Low, like below sea level, right? So I'm really going to have to raise up below it to get through. So the boiling of water is going to be required to happen at a higher temperature. So whatever I was explaining was number 18. Water could be made to boil under increasing air pressure. Yeah, always true. 18A or 18. 19. NT, good. 20. AT, 21. NT, 22. AT, cool. Go to 28 now. 28. Alright, what do you guys get for 28? A, B, C, or D? I'm looking at 28, the multiple choice. 31. My bad. What numbers are for you guys? 31. 31. A. Average kinetic energy is greatest whenever it's in a steam form and when it's at a higher temperature. So what is it? 32 for you guys. D. Good job. That's what we're talking about today. D. 30. My bad. Next. D. Yes, the temperature at which motion ceases. Motion ceases not at 0 degrees Celsius, but at 0 degrees Kelvin. That's the absolute zero. 31. Next. 34. 34. C. Good. Next. B. Particles of matter are in constant motion. That is something that's true for all states of matter, not just gases. Like you right now, you're moving. 35. 36. C. Good. Next. A. Next. Yes. No, sorry, that next would be. Next again? A. What number is that? 39. Okay, next. B. Say again? B. B is in boy. Okay, B is in boy. Next. 41 is B. Good. 42. C and 43. C. Right, C. Whenever gas molecules are coming just off the surface, that's evaporation. When it's starting from the bottom and then we're here, it's boiling. That's coming through the surface. Through the column of water. Alright, so start chapter 13. Good, keep on your desks. You guys should have checked as we went. let us. What do you guys feel? We have a couple like mathy things to do today. We'll take breaks in between. Do you want to play Kahoot now or Kahoot later?
Oh, later.
Raise your hand. Later? Now. Okay, we'll do it now. That's cool. So, pull out a device. If you would like to sit with somebody, you can sit with somebody. Or you can sit with somebody and just put both your names in. If you want to work with somebody, just put like Alyssa Natalie. Whatever. Analysis. Okay. Alright, you gotta hurry up though. Hurry. Alright, I'm going to launch this. Here we go. You guys are going to Kahoot it. Kahoot.it. If it's not, is it loading? If it's painfully slow, then we're going to painfully shut it off. I'm giving you like a minute or two to get it logged on. Yeah, if you can hurry up and get on there. All right. I can figure out most of these. All right, I got 15 people. Can I get like 2 more?
Struggling.
Huh? No, unfortunately. No, we're in the same boat.
Why are there 2 hands?
All right, I'm going to keep the game pin on the board for you. But we're starting this thing, man. I want to use this as review and intro for our next bit that we're going to talk about. I love gas balls. They're pretty easy. So I feel like once you get your math, you get your math.
Work together.
And thumbs up.
Wait, we're working together. It's on load as soon as it's changed ready. So.
Okay, max invisible.
Yeah.
Okay, work together.
There's a silent T. Yeah, there's a silent T. Yeah.
Okay, are you ready? Are you ready?
He loves me so much that he left his bag in my room.
Yeah. Oh, look! You missed the question. I don't have the sound on. Hold on. Water droplets appear by the window. Shoot! Look, I have music on still. Just give me a second. I like this music actually. I know music. Okay. What? Whoa. Do not put evaporating water. That's the opposite. Okay, cool. That's all I need to say. Yes. Oops. What law is represented by the picture? Man, I don't know. Yes. Good. You know P and D, Boyle's law. Keep it up. Right, you gotta be quiet a little bit afterwards. Yeah, keep it up. Which of these can be compressed easily? All right, I'm gonna speed this up. Let's go. This is so easy, guys. You better not get this wrong. I will punch you. Oh! No! Solids cannot be compressed. Why?
Because they're too dense.
They're already like that close to each other. There's no space in between them to compress anymore. What would happen to the pressure of a gas in a steel tank if it was heated? Okay.
14.
Woo! Yeah, that's pretty good right there. Pressure increases. Okay, pause. Why is pressure increasing when you increase the temperature?
Because it's a sign that there are more collisions.
Because there's collisions in the container wall. Good. Nice. Which of these takes the shape of the container it is in? E. Which are you? 11. Alright, please forward. What? What is this nonsense? You guys know, like, okay, I can see where we put only liquids for some reason. Nah. But liquids and gases for sure, but liquids don't take up the entire shape, but they do take up the shape. So I can see where that's a little iffy. But you guys can kind of see, mainly gases, somewhat liquid. Temperature and pressure are blank for you.
It's a good picture.
Increasing temperature.
It's okay. It's okay. It's okay. We got this.
Increasing temperature does what to the particles?
Increase.
Makes them bounce faster. Bouncing, colliding is pressure. Good. Yes, good job, guys. My leaderboard. A gas will always occupy the total volume of a container. True, false, maybe, don't know. Yes, of course. No, always, guys, always. Gases they don't discriminate. They check all the space. They don't go like, I don't like that area. No, they're going to live there.
On the left side of it.
What would happen to the volume of gas if they balloon, if they were heated? Annabella. Isabella.
Coming back
The
again.
balloons. Yeah. Whose law is it not? Well, I think we got to do a couple more. Work with me vocally. Whose law is this? Whose law is this? Charles went to Virginia Tech. Yes, V&T. Good. Keep it up. What is STP? All right. Telepathically tell me if yours is not working. Surprise the pressure.
We're not
You know
doing
this
the
is-
other spot.
You know what this is. I'm not going over that one. Which state of water do the particles move about most freely? I'll just do that. I like this guy. I like that guy right there.
Looks like a dark night.
He's got pimples.
Again.
Good. These are so easy, guys. I'm not going over them. They're easy. Was it what is there between the particles and the gas? Can't tell. Okay. Good job. No, there's no air. Air is gas. People, air is gas. You can't have air between gas because it is gas.
Gas between gas.
I think ooh, I'm not going to do those. I'll stop after this one. Okay, Lusac, describe. That was one of the last ones we went over. We don't know all of our gas laws yet, so let's go, people. Let's do one more. One more.
Uh-oh, please. More. We need more.
If the pressure of a gas goes up by 5, the new volume will be. If it's multiplied by 5, it comes to the volume.
Oh no.
Ooh, that was ugly. Hold up. Okay, stop on this one. Why? How can you just math really quickly in your head?
I guess. Pressure.
If it, hold on, pressure and volume are how are they related? Indirectly related. So if one is multiplied by 5, the other one is divided by 5. It's an indirect relationship, like 1 over whatever we multiply by. That's how 1 over 5 is easier. Okay, that's it for Kahoot for now. I'm going to stop it for now. I'm just going to keep it running. You can keep it running in the background. Are you? Ooh, I'll have to hold that for now. Hold that thought. Hold that thought. I do have candy. That's a good thing. Pull out 1 through 16 for me. Let's go over number 10. Just put your phone to the side. We'll try to finish later, but I want to make sure we have time to practice today as much as we can. So I wanted to walk through number 10 because I know this is the one that I need to go through. Sure. And it might be because I've solved it like 12 ways now, but this is the best, most concise way, even though it doesn't look that concise. Okay, so on the other ones, you should be able to check yourself before you wreck yourself, making sure that you do convert to Kelvin every single time. This one includes some old stuff, like the percent yield. So I'll kind of walk you through the information. Student A has 5 liters of gas at their temperature of 298 Kelvin. Student B had 4.85 liters of gas at their temperature of 295 Kelvin. The question stated, the question said at STP, the theoretical yield was 490 or 4.97 liters. At STP, though, you'll notice that these people are not at STP. So what is it really asking? It's really saying, at STP, what should student A and student B, what should their volumes be? That's the real question. And so volume 2 is what we're looking for student A and student B. So there's like 2 questions embedded into one here. So student A, if you'll notice, I have V, I have T, and I'm looking for V, and I'm also given T kind of, what is this new T though? What is STPT? 273 Kelvin, right? So I'm actually technically given T2, just like between the lines. So I set up whose law? Nope. He went to Virginia Tech, right? Okay, so went to Virginia Tech, VT. I rearranged to solve for V, plug my appropriate values in, and I should get the actual yield of student A to be 4.58 liters. That's adjusted to STP. That's like reaccounted for when you change your temperature sum. Same story for student B, using the same formula. V2 is equal to V1 T2 over T1. Solve for V2 to be 4.599 liters. And I just stretched it out since I didn't want to round too soon. So if these are their theoretical, these are their actual yields, how do you get percent yield? Divided by theoretical, right? So I took their actual yield, 4.58 liters, divided by the theoretical yield given to me in the description of the problem, times by 100. Student A got 92.15% yield. Woo! Pretty good. Oh, but student B was a teeny bit better. When I did student B's actual yield, 4.599, divided by the theoretical yield of 4.97, times 100, they got 92.5. So they would get more money. They would not. Lame. I know, but they still did really good. So what would be a description or an example of a decomposition reaction that these students could have been actually experiencing with? Not everybody at once. Yeah. My favorite one, okay, so you said calcium chlorate decomposing to what? Right, and so why did we have to choose a decomposition like that? Because the problem set up. Right, so you just could give any example of a VCE where it makes a gas. Because these are gas law problems and they're collecting gas, so X number of liters of gas. So that would be a good one, and then you balance it. Oops. Is that right? Yeah. So, any other questions on 1 through 16 right now? I'm now going to do number 12. Yeah? We'll go with 12? Okay, I'll do that one right now, and then we'll kind of keep working through some of these. But these you will have more practice with as we go. I don't feel like this part was horrible, right? On a scale of 1 to 10, between that and stoichiometry? 11. Feeling good. Okay. Hopefully. Let's keep looking here. Okay. So calculate this, number 12. Calculate the temperature of nitrogen gas. So what's our question? So question is T of nitrogen gas. V is equal to 2 liters of the gas, and then STP. Did I copy that whole question? Calculate the temperature of nitrogen gas. 2 liters of the gas at STP is subjected to a pressure. So STP is subjected to a pressure of 9.2. That thing. 920 millimeters of mercury. Okay, so what gas law do you kind of see here? Huh? Okay, because we're given STP, so we're given temperature and pressure and volume, and then we're given pressure and temperature. So what are we missing? Actually, I'm sorry, we're solving for temperature. This looks weird. Oh, no, I know what you're missing. What is the other V? I feel like I didn't copy this whole question, guys. Hold on. I feel like I'm missing like a significant portion. Am I? Let me see. Calculate the temperature of nitrogen gas if 2 liters of the gas at STP is subjected to a pressure of 920 millimeters. Right? So if you know that you've got combined gas law, P1, V1, T1, tell me P2, V2, and T2. What do you know so far? Right, so you know the pressure and volume of P1, or you can really decide which one you want it to be. I chose T1 to be 273 Kelvin because it says STP first in like the first scenario. And it's given to me with this other information, so it's given to me with V of 2 liters. And then pressure is STP. So I'm going to stick, you could say 1 atmosphere, but since we're in millimeters of mercury here, I'm going to stick with the millimeters of mercury standard pressure. So that's 760 millimeters of mercury. Okay, so what else do we got? We have P2 of 920 millimeters of mercury. And what else? Oh, it doesn't say a volume change, guys. That's why you're confused. And I'm sitting here looking again for it. This one, since it doesn't indicate that the 2 liters of volume is changing at all, it doesn't give us any indication for that, you can assume that this is the same. Well, if this is the same, then whose law would this really be if you're considering this to be constant? Yeah. So you got P1 over T1. Is that what you're going to say? Thank you. So P1 over T1 equals P2 over T2. And we're solving for T2, right? So P1, T1 equals P2 over T2. And then T2, what is that rearranged?
T2 equals P1 over T1. P2.
So P1 over
T1, P2.
No, it should be P2 T2. It should be P2 T1 over P1. Right? This is the cross multiplication thing again. So how do I solve these? I take these two and multiply them together. So that's P1 T2 equals these two multiplied together, P2 T1. And then what do we isolate? T2. So then how do you do that? Divide by P1. So those cancel. So then T2 equals P2 T1 over P1. And then just be deliberate about making sure you put your units and canceling them out as needed. And that answer is T2 is equal to 330 Kelvin. Okay. So hold on to 1 through 16 at your desk for right now. And I'm going to come around and check for completion. You guys should be able to ask questions if you need to during teal. Come like whenever you really need to, because I've got duty in the media center during A, but that's besides the point. Okay, let's kind of stop for a second, push that to the side. We've got notes on the kinetic molecular theory, and on Wednesday we're going to kind of continue talking about like the theory of this. But while you're pulling out your notes and stuff like that, somebody just give me a quick description of what a theory is. A theory. Your best guess is kind of not always. It's that plus more. Yeah. Right. So a lot of times our theories are not proven; they're supported. So like the theory of gravity has not technically been proven, but all evidence points to it being true. Stuff hits the ground. You fall out of your chair. You don't levitate, right? There's tons and tons of evidence that proves that to be true. Wait, you're gonna have to, yeah, I'm in the middle of talking. Whenever we talk about theories, it's just generally a hypothesis that has lots and lots and lots of evidence to assume that it is true. So, theory. And another thing about it is that it serves to explain. It's a long-winded explanation. Okay? So, it's a long-winded explanation. It's generally going to be, I don't know how you feel within the book. But a law, that actually would be the law of gravity, but a law is more of a statement. Okay, whereas a theory is an explanation. So, chemists like to use theories because if we use theories, we assume all these little characteristics of gases, for example, we assume them to be true all the time. But we all know, for every rule or law, there's always exceptions, right? But we try to avoid those exceptions because if we start to account for every little difference and every little exception, we have a lot of rules to remember. We have a lot of mathematical relationships we have to like adjust. So we like to pretend that everything follows the theory. Everybody follows those rules. So while you're before I go to Close your eyes. Guys and girls, whichever you prefer, visualize and think about your ideal man or woman. Oh yeah. Thinking about it, right? Okay, ideal. She's perfect in all ways. Okay, let's see, I'll talk about my husband. He gets up, he before we go to bed, he makes coffee every day, and he puts cinnamon in there. Cinnamon, people, that's love right there. Okay? He does the laundry on the weekends for me. He drives me everywhere because I don't like to drive. Like, we're going to the Outer Banks this weekend for my marathon. I might die, but we're going to make it down there because he's going to drive me down there. Then we'll grade your papers on the way. Ideal, right? He feeds me. I don't mean it, but he does. He feeds me. Yeah, so, I got on mine. Anybody want to share? Let's keep PG-13.
No.
Okay, so, but there are exceptions. Like he's kind of gross. He's a guy. I mean, guys are gross. Just a generic stereotype there. Let's see here. He's sometimes lazy and just wants to watch movies on the weekend. I'm like, I want to go do things. Like, there's always exceptions. So there's not really that true ideal guy or girl out there. There's going to be some things you got to compromise on, right? Well, just like gases, right? There's these things called the ideal gases, but they really don't exist. They really don't. But we pretend they exist so we can live in this great la-la land where everything follows the rules that we want. Okay? So ideal gases truly do not exist, but we pretend they do to keep our minds happy, our math easy, and our chemists doing chemistry. Because sometimes when there's too many exceptions, there's too many little different rules to follow, you just kind of say, flip the table, I give up. So we're going to talk about what we assume about ideal gases, and then what really happens in the world. So these are on Reading Guide 14 too, so these might be a little familiar. A little bit. So abbreviate where you need to. So the first one you'll say, ideal gases have no volume. Well, that's probably a lie. Everything in the world is made of matter, and everything that's matter takes up space. Well, if you take up space, you actually have volume. But we assume they have no volume because the volume of the container, we want it to be the volume that the gases can move around in. So if the gases are actually taking up a portion of that volume, the volume's no longer 5 liters. It's like 4.98 liters. And then we got to make adjustments in the math and everything. So we assume they have no volume. So the volume of the container is assumed to be whatever the volume, we say the volume of the container is. Ideal gases are in constant random motion, meaning that they don't collide with, they do collide, but they constantly are moving around and around and around. They collide with the size of the container. When they collide with other objects, though, other gases, they have these things called elastic collisions. Okay? Elastic collisions means whenever a particle hits another particle, 100% of the energy is going to be transferred to the other one. So you guys have seen the Newton's cradle, little beads that hit each other and pop like this. If 100% of that energy was transferred to the other bead that was going like this, it would never stop moving, ever. Years, eternity, centuries. But we know that some kinetic energy is technically lost because it actually ends up, when it loses the kinetic energy, it will slow down and eventually stop moving. But we assume that no kinetic energy is lost to keep our math easy. If not, we got to account for every little detail that's different. The last couple ones are pretty easy. This is one that we just saw on Kahoot, on problem set 13. Kinetic energy is proportional to the Kelvin temperature. So if you increase kinetic energy, you increase temperature. Or increase temperature, increase kinetic energy really is more the direct relationship. And then lastly, stuff doesn't interact with other stuff. But we have these things, it's a 3-letter word that talks about how molecules interact with other molecules. What is that called? Molecules interact with other molecules? Intermolecular forces, right? So we assume they do not attract each other. So we assume no IMFs. But you know what assuming does? That's probably a little bit of a lie. But we assume that they don't interact so we can keep our math easy, and we're going to get to the math in just a second. So what can you imagine is really true about about real gases? Let's start from the top. Real gases have volume, right? You're like, all right, so we're just going with the opposite. I get what the game we're playing here is. They have volume. What do you think about the next one? All right, so sometimes not random, because sometimes they actually interact with other particles and they stick together like glue and they start to collide together, and it's no longer random. There's a reason why they're sticking together. Gas particles have elastic collisions. Nope, inelastic. Because eventually they will start to lose energy and slow down. Ideal gases are proportional to temperature. Yep, that was actually true. Actually true. And then the last one, what do you think? Do they attract or repel? Do real gases attract or repel? Yeah, real gases are opposite of ideals. You'll notice that kind of trend going on here. Ideal gases, we assume they have no IMFs. Real gases have IMFs. So give me an example of a gas particle that is polar. Think back to those Lewis dot structures. Think of how is it polar? What are some characteristics? Huh? Polar is actually unevenly spread out, right? That's where you have one side with more negatives and one side with less negatives. What was one of those?
How about water?
Water. Perfect. Like the example that everybody should know from 8th grade on, if I can get this board to work, is water is polar, right? It looks like this. There we go. Negative side up here, positive side down here. Okay? Water can interact with other water and other water vapors, and they could connect together, and maybe they don't move as fast. Maybe they don't collide as much. Maybe they don't leave their container as much. That's why you can actually leave a cup of water on the desk, and it's still there when you come back. Like the water, not the cup. The cup is still going to be there. That'd be weird. It'd be a mystery. But the water's still in the cup. If you put ammonia, or let's say something like carbon dioxide, let's go with carbon dioxide. Carbon dioxide, is that polar or non-polar? What does it look like? Remember? Double bond on one side. Guess what? Double on the other side. There we go. So, polar, non-polar? Non-polar. Okay. Non-polar. Oops. Not polar. Non-polar molecules, do they interact well with each other? Do they stick well to each other? No. They have those London dispersion forces that are pretty low on the whole strength scale. So if you had some liquid carbon dioxide and you put it in a cup, you walk out of the room, you come back, it's probably close to gone because it starts to evaporate. So there's these particles that we assume they don't interact, but really we know they do. So we know a lot of chemistry at this point. We're almost like full-blown chemists here. Okay, so how can I get real gases to act ideally? Act like those postulates that we just said, those characteristics we just said. The two environmental conditions we have to make sure that they're exposed to are, what's one of them? It's in blue. High pressure and low temperature. Okay, so think about it like this. If I have, let's see, and this is actually one of it. This is the real gas scenario. If I want ideal behavior, so if real gases are most real they act most real at high pressure and low temperature, what do you think what conditions would make them act most ideal? Low pressure and high temperature. Here's why. Put your box of air. Okay, make it a low pressure condition. Low pressure. Okay, they're all spread out, right? Do they interact with other gas particles if they're all spread out? Not really, right? Okay. So low pressure is spread out. So they have no time to really interact or no opportunity to interact with other gas particles, so they act ideally. They don't have any friends. High temperature. What did temperature directly relate to according to those things that you just wrote down? Kinetic energy. What is kinetic energy? Energy of motion. Okay, so here I go. Energy motion. Woo! Okay, really high temperature. I didn't like say hey to any of you guys. I just flew right by, right? Don't have no time to talk to you. So high temperature, no interaction. Low temperature. Thanks. Cold preach. Okay, a lot of time you're just chilling, you're interacting with other gas particles because you're so slow, you actually probably stick to them like glue. I didn't even scare you. So, high temperature means they move so fast, they don't have time to interact. So these two conditions means that they're going to act ideally. These two conditions, when they're high pressure and they're really close together, and they're moving really slow, means they're going to have time to interact and therefore they're going to act real. You got me?
Got you.
Two conditions. Okay. So, you guys, there's this actual law called the ideal gas law. Have you heard of it? Yeah? Yeah, what is it? I'm waiting for your photable to pop out. Yeah. PV equals nRT. Oops, sorry, let me go that way first. PV equals nRT. You've got to know that one because that is going to be your BFF. Because if I say something acts ideally, you get to use this gas law. If I say something acts real or unideally, you got to use some crazy gas law you would learn in AP chemistry, and nobody wants to use that. There's a lot more to it if you assume that they don't act ideally. So, the ideal gas law, PV equals nRT, has those variables that we've already mentioned. P, V, N, and T, except has one new constant, and that constant is called the universal gas law constant, R. R. And R has very special units. There's a couple varieties of them, but this is the one we will always use so that you will never mess up. You will always get it right, and you're going to love gas laws, because they're really not that bad. So the units are the whole R thing is 0.0821 atmosphere liters per mole K. So the number goes on the numerator. Okay, so using that logic, what do you think pressure has to be measured in if you're plugging into this formula? Pressure. Has to be in atmosphere. So if I give you mmHg, you got to convert. Okay? V has to be in liters, amount, moles, and temperature, Kelvin. You can't go wrong with the ideal gas law as long as you convert to your appropriate units. Yeah. KMT is the kinetic molecular theory that we just talked about. Those ideal, all those postulates, those characteristics for ideal gases, they're according to the kinetic molecular theory. So that's what this was. Okay, the kinetic molecular theory of gases right here. Okay, I'm going back. Hold on. Just wait a second. Okay, so using this, let's go ahead and do number 17 together. After 1 through 16, there's, guess what? 17, 18, 19. So let's do 17 together. And I want you guys to take a minute, practice with the buddy. I'll leave you alone for a little bit, and do 18 and 19. Okay? We're getting there. We still got like 40 minutes. I want to make sure we have time to practice everything. So what does 17 say? Let's see here. 17. That's my favorite number. It is. What's my number in 5th grade? My sister's number 18. These are numbers. You guys have numbers too, right?
Those 3, 4.
See, you act like I'm crazy because I remember. All right, I can't find mine. There it is. Okay. 17. A student. This could be you guys. A student collects 425 milliliters of oxygen gas. Okay. Tell me what that means. Volume. Okay, so right now, you writing down all your givens. 425 milliliters of oxygen gas. And then, why are we changing it to liters? Because that's what the ideal gas law likes, and if it likes it, it gets it. Okay, that's what it likes. That's oxygen gas. At a temperature of
24 degrees Celsius.
24 degrees Celsius is technically
90
7 Kelvin. Good. 273 plus 24. And a pressure of 0.889 atmospheres. Okay. How many moles? So what's my question? So what variable? N. Okay. How many moles of oxygen gas does the student collect? Okay. And then it says, second question, how many grams of oxygen is this? All right. So we can convert if we need to. All right. So if you've noticed, there's no second T, no second V, no second T. And I'm telling you right now, it's the ideal gas law. But if you solve this, could you pick out this was the ideal gas law? Right? There's really no other way to go about it. There's no Boyles, Charleses combined. It's like, I got one of everything. It must be the ideal gas law. So, do yourself a favor. Write out PV equals nRT. Isolate what? N. So, what do I divide by? RT. So, N of oxygen gas. This is like the moles of oxygen gas. I'm just denoting it a little bit more. Yeah. R is, what is R? You just write it down. 0.0821 atmosphere liters per mole K. It's that huge unit. This guy right here, that one. Okay, so N is equal to PV over RT. And you got to write your units. If not, you'll probably maybe accidentally later on in life, that chem life this week, forget to convert. So there's my liters. Don't know why I skipped pressure, but here's my pressure. 889 ATM over 0.0821 atmosphere liters per mole K, and temperature of 297 Kelvin. Whew. It's a big, there's a lot of units there, but I'm just taking what I wrote and plugging them in. What units cancel? What units cancel? So Kelvin on the top of the denominator, and then the denominator of the denominator. Okay? Atmospheres in the numerator and in the denominator. Liters in the numerator and liters in the numerator of the denominator. Just top and bottom, right? So what's left? Moles, right? Molecules, it's all good. I'm just joking. So moles are left, and moles in the denominator, actually the whole floppy dot chop thing, it comes up. Copy dot flop, thank you. So moles come up, and we're stuck with moles, which is good because N is measured in moles. What did you guys get? What you get for moles? Make sure you put parentheses around your numerator and denominators. Everybody should be trying this. You're just gazing into the sky. If you do not try this, you're going to get many homework questions wrong because you don't know how to plug in your calculator. Just saying. Anybody? It's going to be a small number. Hannah, what'd you get? 0.0155 5 moles? I'm just going out some so I don't have any round the error. Yeah.
I didn't get that.
Parentheses on top, parentheses on bottom. Did you double parentheses to keep the denominator in the denominator? That's usually, like, not only would I put parentheses here, as I would do like a bracket or parentheses down here. Because basically when you do these multiply by each other and then you divide and then you multiply by that, it's issues. So just double check. Okay, so regardless though, you can play around with that until you figure out how to use your calculator. You should get that number. But that's not our final answer. What did it ask for secondly? Grams. So what do I do to moles of oxygen? Multiply by 32. Good, because 32 grams per mole, 1 mole of oxygen, is the molar mass of oxygen. So then what do you get for grams of oxygen? How much? 0.496 grams. Got it? Okay. So So this is just old stoichiometry stuff, right? That's just popping in every now and then. Okay, take 8 minutes and go through 18, 19. If you need to get up and move around, do that. Use your calculator. 18, 19 right now. But we are finishing notes, so let's go.
Oh, off the mouse. That's a 20.0 meters. Pressure.
0.081 is a constant number. It's not about atmospheres. Atmosphere liter per mole K is a huge unit that collectively describes that. This whole thing is R. This whole thing right here. Okay. But that number is a constant, like the constant for speed of light, 3.00 times 10 to the 8th meters per second. That is a constant, but that number is reflecting all of these units, not just atmospheres.
So we always. What is the pressure? Expressing KPI.
Just make sure it goes back on my desk because I'll forget, you know. Okay.
NRT over Which one are main liters? Or I believe so. No, wait, yes. I cannot ATM so it's KPIs. What is this one? Why are they brackets? Oh, I did the wrong thing. Yes. There we go. Now what is this? You did it. Put this one for Steve. How is this syntax area? 6.11953. You didn't put all of it. Oh, you done 0.082. And then some things I'm going to say it goes down to 6.112. And then 6.12 is moles cancels. Liters or ATM down? I think atmospheres are no, sure, yeah. So ATM. 0.11. And we're looking to put it into KPA. Wait, 620.06. Let's just make sure we get a rate. That's the meters, the liters. So that would be 0.1 now. Okay, in a very large system, we big that's 2 times 62 grams. Oh, that's a mouth, and then you're gonna change the moles.
If that helps to see it like that.
Oh, this is
That might help a little bit. Alright guys, what did you get for the number 18?
620.
620
061.
kilopascals?
Yeah.
Has anybody gotten as far as 19?
We were just starting.
Okay.
So that would be the pressure. And we're looking for molar mass. So we're looking for well, we can't change grams to moles because we don't know how much the...
Can you, but what are the units for molar mass?
Oh,
What are the
moles?
units?
No? Grams, grams per mole.
So how do you get molar mass?
Like grams for the moles.
Didn't you have both? You have both.
What?
You have both of those units. Right?
We have grams per...
And you have... Or did you calculate moles yet?
Not yet.
Okay, calculate moles first.
Oh, that's the LT also.
If you need help on number 18, it is solved for here, but I'm expecting that if you realize that you have one variable that is unknown, you solve for that one variable. In this case, the question was a pressure, so using P equals RT, isolate the variable, making sure every unit is just like the R units are, atmosphere, liters, moles, and K. And then once you solve for pressure, everything cancels except for ATM, which makes sense because you're solving for pressure. The unit should be a pressure unit. And you get 6.11 atmospheres. But the question asks for pressure in kPa, so then you have to go one step further using your dimensional analysis conversion of atmospheres to kilopascals to get 620 kilopascals. You got that all without me. Oh yeah. Okay. How's 19 going? Where are we at right now on 19? You got moles. If you feel like you can get to moles, then you already can get to molar mass. Because what are the units for molar mass again? Grams per mole. Or grams given to you, number 19. Yes. And you calculate moles, yes? Then how do you get molar mass? Just divide. Just take that gram number over that mole number, and that's going to give you the molar mass of that substance because they're equivalent. That many moles is equal to that many grams, so that sets up a situation where you can actually solve for molar mass, not be given molar mass. I'll set that one up. If you got number 19, then sit there and look happy for a second. Look at your foldable, but I'm going to show people how to solve this. This is number 19. So for number 19, I'm expecting that everybody can set up meaning set up the givens. So a student collects gas from decomposition, 100 milliliter of a gas is collected in a very large test tube. The weight of the gas in the test tube is 2.62 grams. So that's my mass. The gas was collected at that pressure and that temperature. What is the molar mass of the gas collected? So I want you to write down a little note for yourself. Anytime you're asked for molar mass, then you should think about what are the units for molar mass. Well, they are grams per mole. So which of these do we not have? Moles. So we have grams. Our question is really, what is in? What is moles? That's our real question. And then we're going to plug it in and find molar mass. So you kind of have to read between the lines a little bit first. But then once you get that, you learn kind of the different types of questions that can be asked of you. It's no longer a question. You know what to do. You get your moles by doing PV over RT when you rearrange your variables. Plug in your P, but your P has to be in what first? Atmospheres, right? So that would be when you convert. How do you convert to atmospheres, by the way? How do you take this to atmospheres? Right. Multiply by 1 atmosphere over 760 millimeters of mercury. So that is 0.918 atmospheres. The V is what? 0.100 liters, because that is this in liters. And then over R, which is 0.0821 atmosphere liters per mole K. And then temperature of 283 Kelvin. So everything should cancel except for moles. You should get moles to be what? Some people who got it? So 0.03953, I'm stretching it out some here. And it should be a really tiny number. Like it says, like 2 grams, almost 3 grams of substance is a really small amount of moles. So that's what you get for moles. Then how do you get molar mass? Right, we'll divide grams by that, right? Because it's got to be grams over moles. So it's got to be 2.62 grams, which was given to us in the problem, divided by the moles that you just calculated. And I just didn't round in between because I didn't want rounding error. So then what do you get for the molar mass? $662. I'm just going to round to 0.8 grams per mole. So this is a huge organic substance that's a gas apparently here. Huge compound. Okay. Look at number 20. Read it. Tell me what your givens are. Oh, hold on. Tell me, like, literally tell me. And I want everybody to make sure they're looking at number 20 and writing this one down. This one's a different one, okay? So 20, here we go. And I'll get you my pretty things. Apparently my handwriting is not very good today. Okay, so there's the very first thing that's given to you, though.
The BCE.
Yeah, actually, there's a BCE kind of indicated for you to write first, right? So let's write that down. Mg. CO3, so magnesium carbonate. What does it decompose to? Carbonates decompose to carbon dioxide and magnesium oxide, metal oxide, and it's MgO because what happens to their charges? They reduce down to 1. Okay, is that balanced? Yep, it sure is. 1 to 1 to 1 to 1. All right. Now, so they're collecting that gas. What gas are they collecting? CO2, right? You know this is solid magnesium carbonate. Anything that's ionic is solid. The only gas here is carbon dioxide. So you know how to do that. All right. Then you also know the rest. You know, tell me the givens now. V is
305
milliliters. Okay. So yeah, so good job, 0.305 liters because we need to probably convert to liters. What else? So what's 22 degrees Celsius? 295 Kelvin. Good. So 273 plus 22. And what is P? 99.8 kilopascals. And I want to convert that to atmosphere, so how do I do that? So I know it's 1 atmosphere over 101.3 kilopascals. Good. And what is that in atmospheres, anybody? 0.984 atmospheres. I got 5. I got 5 as well. I'm just going to put a 5 there. It might be just a calculator error. There we go. Or maybe use 325 instead of 3. Okay, anyway, we've got pressure. We got temperature, pressure, and volume. What is our question here? Ooh, our question, what is our question?
Grams of carbonate.
Grams of carbonate decomposed, right? So, I can get some page space here. The question is grams of the magnesium carbonate that decomposed. But this, what kind of problem is this? Given this information here. This is a ideal gas law problem, right? You have to be dealing with gases in the gas law. You cannot put solids or liquids in there whatsoever because it's all based off the characteristics of gases. So what gas are we talking about all right here?
Carbon dioxide.
We're talking about carbon dioxide. So what am I missing? What variable am I missing? Say again? Amount, right? So what variable is that? N. So my real question is moles of carbon dioxide. Well, in the end, my question is not about carbon dioxide. So how am I going to get from carbon dioxide to magnesium carbonate? Mole to mole ratio. And then you could go from moles of the magnesium carbonate to grams, how? Moles of magnesium carbonate to grams, molar mass. You guys already know how to do this. I probably didn't have to walk you through this at all. But I just wanted you to think ahead before you started calculating so that you're like not really just going with the wind. You have a reason for it. So let's go ahead and find moles of gas, and let's backtrack to moles of magnesium carbonate. So PV equals nRT, nRT. So then N is equal to what? PV over RT. You will write this like 100 times because we've written this like I think 5 times today already. So plugs, how much you putting?
99. Or no.
0.985 atmospheres times 0.35 liters over
0.08.
0.0821.
Over 1.
What's the units?
Atom.
Atmosphere, liters per mole, K, times 295 Kelvin. Cool. All right, what unit is not going to cancel? Moles. And that mole of carbon dioxide we get is 0.0124 moles. Oh, I don't know why I put 5. 4. Okay. Almost there. Remember, our question is about magnesium carbonate, but we could not put magnesium carbonate up here because it's not a gas. So we're talking about gases, or gas is carbon dioxide. Get me to where I want to be. Mole to mole ratio, so what goes on top? 1 mole of top. Magnesium carbonate, because we want to get 2 magnesium carbonate. And then on bottom? Of CO2, because we want to cancel out these moles of CO2. So we get to just straight up moles of magnesium carbonate. But I actually don't need to stop at moles, do I? Do we not stop and take a break? We can just keep going, right? Go to grams for me. What's my last step? Molar mass. So times 1 mole of magnesium carbonate on bottom. And that weighs 84.31. Just so you know. And that gives us our final answer of 1.05 grams of magnesium carbonate. So that would actually be really important to know, like in an airbag situation, if you had a solid and you wanted to decompose to a gas, right? Well, if you wanted a specific amount of gas, like 305, I'm so sorry, that just went by really fast. Oh my gosh, what's happening? Okay, if I wanted specifically 305 milliliters of gas, I would need to know how much of that solid to put in there. If not, it would explode into space. right? That mathematicians are amazing in the airbag industry. Yeah. I'm not sure what's happening here. Okay. So, well, I'm just gonna do it this way. There we go. Okay, so here's what I'd like for you guys to practice for the last bit. Look at ideal gas law stoichiometry lecture problems 1 through 5. You see 1 through 5 on the bottom? Okay, the answers are down there. I think I had to fix one of those. Let me look at mine in a second. It's number 5. I forgot to fix it. I want you guys to start all of those. The number 4. An unknown metal having an oxidation state of +2, 2+, that just means a charge. So if you show them the oxidation state and cross out a charge of +2, it'll make more sense. But I want you to start those at least like if your VCEs are right, because if your VCEs are wrong, it might make your ratios wrong later on. Try those from here now. You guys have about 15 minutes worth of the buddy. Okay? 1 through 5. Oxidation state.
MgCl 2 or 3? But I can check that. So that's 4 ACL 3. So that would be CL3 2, which is magnesium is 2 charge. That breaks down to what's that
These VCs for these, you're going to need a whole page probably, guys. So leave yourself some space.
What does magnesium chloride Mg plus?
You can work with a buddy.
Like MgO plus okay, cool. So MgCl 3, right? Yeah. 2. MgCl 3. You said MgO. Yeah, plus MgCl. Oh, and then MgCl.
So I gotta look for that again. 1 through 16.
Okay. So, that's about at least 2.